Hi, this is Matteo Camilli, and I'm currently an assistant professor at the Free University of Bolzano, Italy. I'm going to talk to you about this piece of work entitled Microservices, Integrated Performance and Reliability Testing. This is actually a joint work between the following co-authors. So we have Antonio Guerriero from the Università di Napoli, Federico II, Italy, Andrea Yanes and Barbara Russo from Free University of Bolzano, and Stefano Russo from Università di Napoli, Federico II. Okay, so before getting into the details of these work, this is the outline I'll try to follow throughout the presentation. So we'll have a brief interaction on microservices and DevOps practices in a context of microservices systems development. I'll be talking a bit about the train ticket benchmark I'll adopt this kind of benchmark to introduce small examples throughout the presentation. And by the way, this is also the benchmark we adopt in our evaluation, this work. Then I'll talk about our approach. So in particular here, I'll describe the definition of the operating conditions, the ex-vivo testing, and the integrated performance reliability analysis. Then I'll talk about our evaluation, so the control experiments we conduct, and then we'll try to draw a conclusion in the end. Okay, so introduction. I'll go very rapidly through these things, but just to introduce a bit of context. So the microservice architectural style is widespread in industry, so it represents a sensitive matter nowadays, and it usually yields better modularity, better maintainability. It favors distributed teams and independent and continuous, integration and deployment practices integrated in a context of DevOps. So what is DevOps? So DevOps is a term used to identify a set of agile practices aimed at continuous interaction between developers, operators, and quality assurance teams, as described in this figure on the right side. So the development stage produces a new version of the target microservices system, and this new version shall be assessed in a quality assurance stage, also take into account the information coming from operations. So in this context, changes are very easy to introduce, but the effect of changes to important quality attributes of the target system are usually hard to understand. But these effects are very important because understanding such effects on the target qualities as well as their inner relationships should guide decisions in the quality assurance stage. So what are these changes? That can be either evolutionary or operational changes. An evolutionary change occurs in the development because of new or modified microservices, for instance, because of new requirements or new or modified user preferences. An operational change occurs instead in operations because of new kind of users, different interaction patterns, modified or changed number of users due to new functionality, piece of functionality, or due to external factors like, for instance, the pandemic condition that could modify the way users interact with the target system. So what are the qualities? So in this work, our focus is primarily on performance, reliability, and their existing inner relationships because they represent, both performance and reliability represent important quality attributes for microservices systems. So the high-level objectives of our work are developing a methodology and testing platform called MIPaRT for microservices in the DevOps context. So MIPaRT stands for Microservices Integrated Performance and Reliability Testing. And with this methodology and platform, we want to support analysis of our target quality attributes with our performance, reliability, and their existing relations. So what is peculiar of microservices in this context is that microservices push a lot the adoption of DevOps practices. In this context, there are fast changes in very short cycles. So there's the need of disciplined and systematic methods to understand and represent the operating conditions, and also methods able to understand the effect of changes of the operating conditions to the target quality attributes. So we have the following research questions. RQ1, so does the integrated performance and reliability testing provide advantages compared to the verification of the qualities in isolation? And RQ2, so can MIPaRT, so our approach, detect existing relations between performance and reliability issues? So to evaluate our methodology and testing platform, we adopt this train ticket microservices benchmark. It's a booking system based on the microservice architecture, and we essentially selected this one because many reasons. First of all, it's a well-known benchmark for research on microservices systems. It's open source and publicly available. It has a pretty standard size for this kind of system, so it contains 40 plus microservices, adopting a diverse set of languages and modern frameworks supporting automated deployment practices in software containers. And it has a very well documented API using the Swagger framework. So here you have we have an example of request for the train ticket benchmark. So we can see that we have a number of examples containing type of request, the core microservices handling this kind of request, the path, the HTTP method, and also a list of arguments with type and also constraint. So for instance, the booking request is handled by the pre-serve service, and it is a post request, and you can also see here the list of accepted parameters. For instance, the account ID is a string, alphanumeric string. It is required. We should also specify the seed type, for instance, that is a string that contains an integer value greater or equal than 0. Then we have the date, that is again a string in date time format, and so on and so forth. Okay, so that's it concerning the introduction. So let's get now into the matter of the MIPaRT methodology. So I'm going to show you an overview on the whole methodology in this slide. So it is essentially a pipeline of three stages as represented in this figure on the right side. So the first stage is the definition of the operating conditions. That is the central concern, as I mentioned early on. So here we extract information from operations and use them to characterize the actors interacting with the target system in terms of amount and also in terms of their behavior. And we also characterize the changes, either evolutionary or operational. So then the second stage is the ex-vivo testing. So ex-vivo stands for any type of software testing performed in-house using information extracted from the field. So here essentially we use the rigorous characterization coming from the previous stage, and we use it to automatically generate and execute load testing sessions of the target system under the given deployment configuration setting. So then we have the third stage, that is essentially the integrated analysis. So here we use the raw measurements coming from the ex-vivo testing stage, and then we execute performance and reliability assessment of the target system. We extract performance and reliability indices, and we create proper visualizations in order to guide the engineers in taking the right decisions. So following the flow on the right side, we start from the usage data collected by monitoring the target system. And from there, we extract a set of behavioral models of the actors interacting with the system. We also extract the so-called behavior mix and a description of the workload intensity. So then we use these pieces of information to guide number of ex-vivo load testing sessions. And out of the testing sessions, we extract raw measurements. Then we then use in the third stage to carry out the performance reliability assessment. And out of the integrated analysis, we extract a number of key performance indices and a number of visualizations to guide engineers in decision gates. So the first stage of the MIPaRT methodology is the definition of the operating conditions. So to define them, we need the specification, first of all. So in our case, the specification describes requests that actors can invoke on a target system, on the system under test. So the specification includes, in our case, the actor or the actors who can invoke that request, the relative path, the parameters, as well as the constraints, and the possible responses in terms of HTTP status codes. So this is essentially everything we need to generate synthetic requests and check their validity according to the answers. So all this piece of information can be extracted from the Swagger OpenAPI specification, for instance, as shown in this slide. And I want to stress that this is pretty common for microservices systems nowadays. Then we build a number of behavioral models that are stochastic representation of the actors according to their behavior observed in production. So essentially, we use session logs produced by the HTTP servers, and by analyzing such logs, we automatically extract these stochastic representation. So an actor, in our case, can be identified according to the semantics of the executed operations. For instance, the registered actor, is an actor executing a login request, for instance, or a buyer is the one executing a buy request, and so on and so forth. So starting from the session logs, that essentially, that contain requests along with timestamps, we can filter by actor, and we can build a graph representation using a process mining approach. So in this case, the graph, each node of the graph is a request, and arcs are annotated with number of invocations. And then we essentially refine these graphs to derive a discrete time Markov chain representation, where each state, so for each where each node in this graph is either valid or invalid according to the values of the parameters and the corresponding constraints of the request. And the arcs are annotated with probability values estimated by computing the frequency of invocation of the requests. In addition to the behavioral models, we also build the so-called behavior mix that associates to each actor its own probability of occurrence in production. So again, from the session logs, we extract the number of sessions per each actor, and we divide it by the number of all sessions in order to derive a categorical distribution associating for each category. So for each actor, its own probability of occurrence. So in this case, for instance, 50% of the actors are guests, 30% of them are buyers, and 20% of them are refund claimers. So the last piece of information we need is the workload intensity. So again, by analyzing the session logs, we extract a discretized distribution of the number of users occurring in production. So as shown by this figure, we first derive the distribution of the workload intensity, associating for each workload intensity the corresponding frequency, and then we apply a data binning technique to derive a smaller amount of discrete workload intensity bins associated with the corresponding likelihood. So by looking at this plot on the right side, we can understand what are the important conditions to be tested according to the likelihood. So for instance, in this case, the bin 200 is very important. It's a very important condition to be tested because it's associated with the highest likelihood. So the ex-vivo testing stage receives as input a number of things to recreate and control the operating conditions. So from the analysis of the operations stage, it receives as input a number of DTMC models that are essentially the behavioral models, the categorical distribution representing the behavior mix, and the set of important workload intensity values to be tested. From the development, it receives as input the current version of the system B and the target deployment configuration. So for each triplet of this type, lambda VC, we execute a testing session. For each testing session, we deploy the system under test version V onto the testing environment with deployment configuration C, and we generate a synthetic workload according to lambda. That is a workload intensity value, and we sample the actor instances according to the behavior mix, and each actor behaves according to the corresponding DTMC model. So zooming in, this is an abstract schema representing what happens inside the load testing module. So we sample the actors and we follow their own DTMC model. And the current state of the DTMC model identifies a class of inputs that can be either valid or invalid according to the corresponding OpenAPI specification. So we use this information to generate synthetic requests, and also to generate either valid or invalid inputs. So for each testing session, we collect the following raw data. So essentially the number of requests per each input class, the response time for each issued request, and a corresponding status code. For each testing session and for each input class, we compute the following two metrics: the performance estimator and the reliability estimator. So the performance estimator is the essentially computed as the normalized distance from a particular performance threshold, LP, that is, for instance, determined based on usability engineering practices. And as reliability estimator, we use the traditional Nelson non-parametric estimator. That is essentially 1 minus the number of failed requests divided by the total number of requests, in our case, for a particular input class. So the integrated performance and the reliability analysis produces the following visualizations. On the left side, we can see the school criticality sector plot that provides a global view on all microservices, and it ranks them according to the criticality level. So in terms of joint performance and reliability estimators. So for instance, the pay invalid class, it yields medium criticality since it exhibits very high performance, but at the same time, it has severe reliability issues. On the right side instead, we can see the radar plots that provide finer information of a given class. So for instance, for the pay invalid class, we can see a very low request ratio and no particular issues. For the pay invalid class, we can see instead, again, a very low request ratio, no performance degradation, but 100% of the requests fail. More than 60% of them are server errors, and almost 40% of them are connection errors. So to evaluate the MIPaRT methodology and platform, we designed a number of controlled experiments where we essentially systematically reproduced two typical DevOps scenarios: an evolutionary change and an operational change. For each one of these scenarios, we deployed the training ticket in our ex-vivo testing environment. We execute a number of testing sessions plus the integrated analysis, and then we observe the results to answer our research questions. So we reproduced the first scenario, the evolutionary change, by testing two versions of train ticket, V1 and then V2. And in this case, we consider the same behavior mix, mixing three different actors: guest, the buyer, and the renouncing. And we consider also three different workload intensity values: low value, 150 users; a medium value, 200 users; and a high value, 250 users. So in total here, we executed 6 testing sessions and integrated analysis to understand possible issues. So here we can see the 6 criticality sector plots out of the 6 different sessions. So something we can immediately see from these visualizations. So in version 1, many classes are in the medium criticality sector. And this doesn't happen in the second version. So in this sense, the second version of train ticket is better than the first one. But in the second version, we can see a huge drop, both in terms of performance and reliability in the last case, in the last session. So some classes here drop into the high criticality sector with the high workload intensity. So further explanation can be obtained by looking at the radar plots of individual classes. So for instance, in this slide, we have the radar plots of the search ticket valid class. So we can see that in version 1, we have the very same performance degradation, no matter what is the workload intensity. And we also have a lot of server errors. And these essentially are fast failures, revealing pure reliability issues with this class. In the second version, instead, we don't have any more these kind of issues, so they have been fixed. But we can observe here an increasing performance degradation over increasing workload. We don't have any more server errors, but we have a lot of connection errors. We have a performance issue that essentially manifests itself at high workloads as reliability issues. So we recreated the second scenario, the operational change, by testing the train ticket version v2, so the same version, under the following workload intensity, 150 users, and we consider two different behavior mix, so two different categorical distribution associating different probability values to the different actors. So in total, we executed 2 testing sessions, and here we can see a very high level summary of the outcomes we obtained. So on the left side, we can see the effect of the operational change on the number of issued requests for each input class. And on the right side, we can see the effect of the operational change on the performance reliability estimators. So we can see, for instance, that after the change, the get voucher invalid class has 0.75 performance and very low reliability. We can also see that some issues remain, and this is due to some similar interaction patterns for some of the classes, even though the operational change. All right, so to sum up, so in this presentation, I introduced the problems in microservices development in the context of DevOps. So here we have very frequent changes in very fast development cycles. So changes in this context are very easy to introduce, but often hard to understand. So MIPaRT, our methodology and platform, helps quality assurance teams to investigate such effects through a rigorous characterization of the operating conditions as well as their changes, and the automated testing plus integrated analysis guided by the description, the rigorous description of the operating conditions. So in summary, in the context of RQ1, we wanted to understand the advantages of the integrated performance and reliability testing approach. So according to our experience, we were able to quantify joint effects of both our qualities of interest, the performance and the reliability. And we were able to detect in some cases cascade effects, and is indeed not possible if we consider the qualities in isolation. Considering RQ2, we want to understand the relations between performance and reliability issues. And again, according to our experience, we are able to distinguish between fast failures. These are essentially pure reliability issues versus performance degradation, causing in turn reliability issues at scale. So the software tools developed and used in this work are open source and publicly available. So feel free to take a look at them and download them, try them, or even contribute if you want. Okay, so that's it. Thank you very much for your attention.